Okay, great. I'm going to be talking about the technological singularity, um, which is not directly about large language models, but I'll say the connection is that a lot of people think that large language models are the most likely road to a technological singularity at the moment. And so when we're talking about changes in the capabilities of AI systems over time, we are kind of probably talking about changes in the capabilities of large language models or systems based on large language models. This is kind of joint work with Tom Davidson at Open Philanthropy. We're collaborating, but most of this is my thoughts, and then I will briefly introduce some of his thoughts at the end. Okay, so why talk about this? There is a long tradition of uh, reflection on the possibility of a kind of intelligence explosion. Recently, the dialectic has changed a bit because David Thorstad published an influential criticism of the idea of a singularity. I'll talk about what a singularity is supposed to be in a minute. Um, and the core criticism is that the growth assumptions underlying the idea of a singularity are unrealistic. Um, and so in the past few years, people have been taking the idea of a singularity a lot less seriously, which is good if it's not a credible idea, but is not good if it is a credible idea because the singularity has a lot of implications for how we should think about AI safety. So there are two goals to the project. In the talk, I'm going to focus more on the first goal. The first goal is um, to show that there are safety implications for singularity type scenarios, even if we back off some of the really strong growth assumptions that have recently been criticized. And the second part of the project is to offer some new arguments that support the strong growth assumptions. Um, and a lot of those arguments are going to be based on empirical data. Um, okay, so here's what I'm going to do. I'm going to talk about what the singularity hypothesis is. I'll briefly survey some like kind of arguments that there's going to be a singularity, but I'm not going to go into a huge amount of detail um, about those arguments. The core part of the talk is going to be distinguishing between what I'm going to call a strong singularity hypothesis and what I'm going to call a weak singularity hypothesis, arguing that actually both are relevant when you're thinking about AI safety, and then showing that most of the criticisms of singularity type arguments and singularity type reasoning only apply to the strong singularity hypothesis. And basically, that leaves us with reason to be concerned about the weak singularity hypothesis. And so I don't think that recent criticism shows that we should kind of stop thinking about singularity type worries. Okay. And then as a bonus at the end, this is kind of more what Tom has been thinking of. I'll talk about some reasons for strong growth assumptions. Okay. What is the idea of the singularity? The idea of the singularity is that as soon as artificial systems start being able to contribute to AI research, I'll call this the big moment. So as soon as we get to the big moment, we're going to see a kind of intelligence explosion. Um, this is a phrase that's often repeated. And the reason we're supposed to see this is because as soon as AI systems can contribute to AI research, incremental improvements in AI systems will lead to incremental increases in the kind of like quality weighted research effort that's being applied to developing new AI systems. So we'll have a kind of positive feedback loop where AI systems rapidly become more and more capable. Okay, and that's what people mean by the singularity. Okay. Like I said, I'm not going to be focusing specifically on LLMs, but they're basically in the background because most people think if we get kind of autonomous research AIs going in the near future, they are going to be based around language models. So I think most people would think that when the big moment comes, uh, the systems that bring it about are going to be based on large language models in some way. Maybe they'll be agentized. Okay. Common themes in discussions of the singularity hypothesis. The growth in capabilities over time is going to be extreme. So people talk about exponential or even hyperbolic growth. Hyperbolic growth leads to a kind of like vertical asymptote on the graph of capabilities versus time, which is an extreme claim, um, not one that I will be defending, but it's something that people in the literature on the singularity do make. So I think Bostrom basically makes this claim or suggests that this is a thing that you might think, and people like Ray Kurzweil make this claim. Okay. The growth will continue until AI systems are way smarter than us, and people say things like, at least as far beyond the most intelligent human as the most intelligent human is beyond a mouse. Okay, again, strong claim. And, you know, the creation of systems like this are going to fundamentally alter human life. Okay. Um, some arguments for uh, for the singularity. There are two kind of like more fleshed out arguments in the literature. One is by Dave Chalmers and the other one is by Nick Bostrom. So this is Chalmers' argument. Um, AI is human level artificial intelligence. So the moment we invent AI is the big moment, basically. And then Chalmers says if there's AI, there will be AI plus. AI plus is AI that is kind of like substantially more intelligent than we are, but not yet super intelligent in the way that this mouse quote was suggesting. Okay. And then if there's AI plus, then there will be AI plus plus, where AI plus plus is this kind of like super intelligent type of AI. So there will be AI plus plus. Okay. Obviously, this argument does not um, show the kind of motivation for the premises on its face, but I've written extendable methods and proportionality thesis here because what's going on is basically like Chalmers thinks that if we get to human level AI, we will probably have done so using a method that we can continue to deploy to make AI a little bit better, to make it slightly better than human intelligence. That's what he means by an extendable method. And then he thinks the way that we get from AI plus to AI plus plus is because uh, every time there is an increase in the capability of AI systems, there is a proportional increase in the ability of AI systems to design more capable AI systems. And this is what he calls the proportionality thesis. And he uses the proportionality thesis to get from a bit smarter than us to super intelligent because each kind of like iterated improvement leads to another proportionally just as large iterated improvement, and so on and so on. Okay. I should say Chalmers is notable because he does not say anything extreme about the kind of rate of the growth that's going to bring us here. He just says soon after absent defeaters, and he can mean anything from in a few decades to, uh, you know, in a century. I don't know. That's he leaves that open. Bostrom, on the other hand, has these mathematical models which do make the extreme growth assumptions. His argument for the singularity is something like the rate of change in the intelligence of artificial systems is equal to optimization power divided by recalcitrance. And when we make better systems, they'll contribute more optimization power. And then he has um, some little differential equations, and then he has these graphs that show a vertical asymptote. Okay, so Bostrom makes very strong singularity claims, okay, about um, how quickly we should expect there to be superintelligence after the big moment. And you can see in this graph, it's less than 2 years um, after the big moment. Um, okay, so these people, I think, have been promulgating what I'm calling the strong singularity hypothesis. which is also the thing that's officially attacked by David Thorsted in his paper. And I'll understand the strong singularity hypothesis to mean that there's going to be prolonged exponential or even hyperbolic growth in AI capabilities. The growth is going to continue until AI systems are orders of magnitude more capable than humans, and this will result in a fundamental discontinuity in human history. Um, I don't really know what counts as a fundamental discontinuity, but I'm not going to be thinking about that too much. We'll just grant that if all that stuff happened, it would be a fundamental discontinuity. Okay, so things to note about the strong singularity hypothesis. It uses a notion of when singularity has been achieved that involves a threshold of intelligence that's just specified as some like huge ratio compared to humans. Orders of magnitude more intelligent than humans, or like as much more intelligent than humans as a human is than a mouse. And it talks about a specific growth function that is held to be superlinear. Okay, so growth is happening at an increasing rate. We're getting faster and faster until superintelligence is achieved. Um, like I said, Bostrom's argument has both of these flavors. Chalmers doesn't say that much about what specific growth function is going on, but he does um, specify the endpoint in this way. Okay, so now I want to suggest that if we're concerned about the singularity because we're concerned about things like human disempowerment or a misalignment catastrophe, which are some of the main reasons that people are concerned about the singularity, then this might not be the best way of kind of like formulating the thing that we are interested in. Okay. In particular, uh, what we care about or should care about should be whether the systems are better enough than us that they can strategically outcompete us or dominate us, and whether the process of them gaining capabilities is happening faster than we can develop effective alignment strategies or institutions that can kind of mitigate the risks. Okay, so rather than talking about the endpoint in terms of some like kind of fixed scale, orders of magnitude above humans, and the growth function as some like particular mathematical function, we may be more interested in thinking about these things as kind of like specified by their safety implications. Okay. So I'm going to introduce a weak version of the singularity hypothesis, which I think does that. And the weak version says that growth in AI capabilities after the big moment is going to outpace our ability to develop effective alignment strategies and institutional safety mechanisms. It's going to continue until machine learning systems can basically do all of the kind of things that people worried about alignment catastrophe or a misalignment catastrophe or human disempowerment are worried about. So strategic outcompete, the ability to strategically outcompete humans, the ability to form and pursue long-term plans, the ability to manipulate humans. Okay. And of course, it wouldn't really be a singularity hypothesis unless the idea was that this sustained growth depends counterfactually on and is partially explained by the AI contributing to AI research after the big moment. Okay. So key things. I think that a weak singularity might be achieved by changes in capabilities that are only a few orders of magnitude or even one order of magnitude beyond what we have now. And the growth rate does not have to be superlinear. Okay, so I think that we should worry about singularity scenarios even when they are way weaker than the things that Bostrom and Kurzweil have been talking about are. Okay. I take it that the weak singularity hypothesis is a logical weakening of the strong singularity hypothesis. So the strong singularity hypothesis entails the weak one, but not vice versa. Okay, yes. So basically, I think, the strong singularity hypothesis is kind of intellectually captivating because it's extreme. But if we are interested in AI safety, then we should be interested also, and potentially just as much, in the weak singularity hypothesis. And so if somebody tells us that there are convincing arguments against the strong singularity hypothesis, that should not be a reason to abandon thinking carefully about singularity hypotheses unless they are also arguments against the weak singularity hypothesis. And I'm going to argue now that most of the arguments that have been given against the singularity hypothesis only target the strong singularity hypothesis. Okay, so we don't have good arguments against the weak singularity hypothesis. And I'm not going to canvass all of the arguments that have been offered, but I'll talk about two that I think have been influential and that are found in the Thorstad paper. One of them is that good ideas become harder to find, and the other one is that intelligence grows sublinearly with respect to other kinds of quantities. Okay. So here's what Thorstad says about the idea that good ideas become harder to find. Research productivity, understood as the amount of research input needed to produce a fixed output, falls with each subsequent discovery. A recent economic review singles out Moore's law as a prime example of declining research productivity. Between 1971 and 2014, Moore's law was sustained across an 18-fold drop in semiconductor research productivity by astronomical increases in the amount of labor and capital devoted to semiconductor research. This situation is unsustainable. Many forecasters think that Moore's law will end in this decade, and most of the rest think it has already ended. Interestingly, there was recently an interview with the head of NVIDIA who said that he thought that there would be like faster than Moore's law predicts growth in the capacity of their systems in the next 10 years. Not because they are learning to put more processors into their chips, but because they're doing other things that have the same effect on computation. But anyway, so the idea here is that the amount of effort it takes incrementally to discover the next thing always goes up. And this counts against the idea that we could have something like, you know, exponential or even hyperbolic growth in basically any kind of capacity or technology development over time. Okay, so I think this is actually interesting, and I've talked to David about this, and I think he was concessive, although he wanted to reserve the idea, the term singularity hypothesis for the strong singularity hypothesis. But so the idea that new ideas become harder to find, and the example of Moore's law does like a reason to doubt that we can get the kind of graph that I showed you when discussing Bostrom, a graph that has a vertical asymptote. But actually, I think that the same example should make us more worried about a weak singularity rather than less worried about a weak singularity, because it's an example in which a kind of exponential growth model for a capability is sustained across many orders of magnitude by society directing more resources to a problem. And so what that shows is that we probably have not gotten close to organizing society, to marshaling all the resources society can organize towards improving machine learning systems. And so we should expect that their capabilities will continue to improve over the short term in a way that is at least maybe linear in time. So I don't think that's a good argument against the weak singularity hypothesis. Okay. The second kind of consideration is that there is sublinearity of intelligence growth in other kinds of growth. Okay. So here's what David says about that. Intelligence grows sublinearly in underlying quantities such as processing speed that have been the targets of recent growth. One way to see the point is to consider performance metrics that might plausibly correlate with intelligence. Here, the story is strikingly consistent. Across almost any metric we care to measure, sustained exponential growth in computer capacities has led, at best, to linear growth in performance. Okay? And again, linear growth in performance is inconsistent with the strong singularity hypothesis because part of that hypothesis is that you have superlinear growth, but it is consistent with the weak singularity hypothesis. And I think if we extrapolate a linear growth of AI capabilities at the rate that we've seen over the last 10 years, we should be concerned about what's going to be available to us in the next 10 years. Okay, so I think a linear growth of intelligence in time based on devoting more resources to other things is enough to get us significantly worried about a weak singularity, about the safety implications of the artificial systems that we're going to be seeing shortly. Okay, so why do we care about the singularity, the weak singularity hypothesis? It does not posit a vertical asymptote in the graph of AI capabilities. Instead, it says that we'll first have the big moment, and then eventually, after not too long, we will have machine learning systems that have strategically relevant cognitive advantages over humans. That's AI safety relevant, but you might think, well, maybe we would get that also without the AI systems contributing to AI research. So why care that much about the weak singularity hypothesis? And I'll give you two reasons. One is that even if AI contributed research effort towards AI development, neither gets us all the way to the strong singularity, nor is necessary to get us to a kind of like AI safety worrisome point. It is going to be relevant because it's going to accelerate the rate at which AI capabilities emerge. And so it's going to be an important part of our mathematical models of the growth of AI capabilities over time. So our models are going to have to incorporate this feature, and we're going to have to think about this feature in order to come up with reasonable predictions about how the capabilities are going to change in time, especially if we want quantitative as opposed to qualitative projections. And second, because I think it suggests interventions that are net AI safety positive. For example, it suggests that we should be especially worried about capabilities research that could enable AI improvements to be put to use designing AI systems in a more or less autonomous way. So it suggests that these specific kinds of capabilities improvements are more safety relevant than other kinds of capability improvements. And that is an actionable kind of thing if you're thinking about policy. So, right. Okay, so that kind of concludes my case for thinking that the Thorstad paper and other kind of criticisms of the strong singularity hypothesis, even if they are successful, do not show that we need to stop worrying about the singularity. There's still the weak singularity hypothesis. We should still be thinking about the effects of AI systems contributing to research on AI. Okay. Now in this part that I've called bonus, I will kind of briefly talk about the other part of the project. And the other part of the project is defending the idea of strong growth assumptions. Okay, so I think we should concede to Thorstad that ideas become harder to find. It's not particularly viable to try to resist that. It's a thing that's been well established in economics, and I don't see why AI would be any different. So as progress is made in a field, marginal progress becomes more difficult. In kind of traditional cases, what that means is that in order to maintain a constant rate of progress, the discovery of new ideas, you need to invest ever more time and resources into the process of doing research. Okay. Or equivalently, if you invest a fixed number of amount of time and resources, you expect each subsequent new discovery to take longer than the next one. Okay. Um, we can measure the relationship between progress and effort by looking at this quantity, the returns to research and development, R, where R is defined as the number of times progress in a field doubles for each doubling of cumulative research and development effort. Now, of course, you can't just directly track progress in a field, so you need some sort of way of quantifying that. But if you have a way of quantifying that, and then you have a way of quantifying cumulative research and development effort, then you can come up with this number, okay? You can generally measure cumulative research and development effort by looking at, for example, how many people are employed in research positions in an industry, and how much they're working. So you can look at the number of hours worked on research and development in this field as a way of measuring cumulative research and development effort. Um, The case of AI research is special because when we're thinking about singularity type reasoning, we're thinking about a case in which the incremental discoveries can be turned more or less directly back into research and development effort. Okay, so whereas new developments in how to build an airplane do not themselves make it easier to research the next new development. Um, uh, in aerospace engineering. In the case of AI, if we're thinking about we're past the big moment, so AI systems can be used to aid AI research. Maybe they function autonomously as little researchers. Maybe they just make human researchers more effective. Either way, improvements in AI R&D translate into, in a rather direct way, more AI R&D power. Okay, so whereas this is not true when we're thinking about other kinds of questions, when we're thinking about AI and the singularity, it matters quite a lot what R is. And if we measure the progress of AI by looking at the quality weighted research effort produced per unit of compute, then it turns out that the key question in thinking about the dynamics of the singularity is going to be whether this number R is greater or less than 1. Okay? Because if R is greater than 1, doubling research effort devoted to AI is going to more than double the available research effort for AI. Because again, R is the number of times progress in a field doubles for each doubling of cumulative research and development effort. And if progress in the field just is how much research effort you get per unit of compute, if that is doubling more, or if you're getting more of that per doubling of total R&D, then than 1, or the ratio is more than 1, then doubling your total R&D is going to more than double the amount of R&D effort you can put in towards the next innovation. Okay, so the key empirical question is, what should we think R is with respect to um, to not just AI research, but the kind of AI research that could be put to use in furthering AI research. So maybe you could think of that as LLM development. Okay. And it turns out that there's some empirical evidence about what R is in related fields that makes it not seem crazy to think that R exceeds 1. Okay. So there have been some studies that suggest that um, the most fleshed out one is this study of image recognition from 2012 to 2022, which looked at the I'm not sure what measure they used of success in image recognition, but it looked at improvements in the algorithms, and it measured the cumulative research and development effort by looking at how many people were employed as engineers working on image recognition technology over that period, and it found that the value for R was 1.4. Okay. And then when you look at a variety of other tasks, you get numbers that seem to kind of like hover around 1.5. Okay, some of them, computer chess seems like it's lower than 1, but that's the exception rather than the rule. Okay. So what's going on here is that it seems like there's some empirical reason to believe that R for machine learning, and therefore for the kind of machine learning that might be useful for improving machine learning systems, is higher than 1. And there's certainly not a kind of like strong a priori reason to think that it's less than 1. And so given these kinds of empirical results, Tom and I think that the idea that it's kind of crazy to think that there could be a strong singularity um, is much too strong. It's not crazy to think that there could be something close to a strong singularity. It's probably something that we should assign uh, a low but non-trivial probability to. And what that means is when you're thinking about AI safety, you can't dismiss the kind of concerns about strong singularity scenarios. Okay. So to kind of recap, recent criticisms of the singularity hypothesis, we think, fail at 2 levels. First, they fail really to show that the strong singularity hypothesis is not empirically, justifiable. Okay, there's some evidence that suggests that it would be kind of par for the course for this kind of thing to happen at least for a time. Obviously, high values of R can't stay around forever because eventually you'll run out of new innovations to discover. But at least for a time, we could have some growth in capabilities well described by the strong singularity hypothesis. Okay, but even if those arguments did succeed, they would still leave the weak singularity hypothesis, and that is still something that we should be concerned about from an AI safety perspective. So the message is it's hasty to dismiss the singularity hypothesis. It's still something that we ought to be thinking about carefully if we are thinking about AI safety. All right, thank you.